This week we're learning about the Millikan Oil Drop experiment, and we'll cover 4 aspects: the history of the experiment, the apparatus used by Millikan and by us to determine the charge on an oil drop, the procedure of using the apparatus, and the physics and mathematics that helps us calculate the charge on an oil drop from the measurements that we take. Details of the history of the Millikan Oil Drop experiment will be given in question 1 and assignment 5, but here's a short summary. From 1908 to 1913, Millikan and Fletcher did the work that resulted in their concluding that electric charge came in smallest fundamental units, that it was quantized and not continuous, that there was in fact a smallest discrete unit of charge that we now call the electron, and they determined that the value of that fundamental charge was 1.592, very close to the currently accepted value of 1.602 times 10 to the minus 19 coulombs. The work was so important that it was in 1923, it was awarded a Nobel Prize. Now let's talk about the apparatus and the procedure that you do with the apparatus to find the electric charge on oil drops. So here's a photograph of Millikan's original experiment. Here's the one that we're using, mounted on the stand. Here's a detail of the chamber. And here are 2 schematic drawings or diagrams that simplify what we're doing. So what we're doing is we're spraying oil into a chamber. The oil is falling through a hole, and the droplets go between 2 plates, which we can charge or not charge, letting the drop fall freely when the plates are not charged, and then charging the plates and being able to make the drop go up or down by the electric force on the charged drop. So that's the basics of the procedure and the apparatus. Okay, here's that simplified diagram expanded. What I'm going to ask you to do is pause the video and look at all the parts, because on a quiz I may ask you to draw a sketch of the apparatus and show all the important parts. So just take a look at this before I explain it and see if you can identify all the important parts. Pause the video and do that. Okay, let's go over it. So first of all, we're making oil drops, so we have to have an oil sprayer, and we have an oil of known density, and we spray it into the chamber and create this mist. Remember, these are tiny, tiny drops, like droplets of fog, and some of them will fall through the hole. And once they're between the 2 plates that we can charge with a voltage source that isn't shown here, we can view them. There's a viewing scope here so that you can see the drops and watch them as they fall or rise, depending on whether you charge the plates and turn the field on or off. There's also a radiation source that I didn't mention. So there's a lever over here that allows us to see the radiation source. It allows us to turn the radiation source on, and the radiation source will help to charge the drops. So when you spray them, the drops will become charged by the rubbing, but we often use the radiation source to put a stronger charge on the drops so that when we turn the electric field on, they'll be more responsive. So make sure you're familiar with all those parts and that you could draw some kind of rough sketch that would show them so that you could explain the purpose of each of them. Okay, here's a second diagram. Pause the video and look at this and just review what we went over and see if you can identify the parts. And this is an example of another simplified drawing that you might do when if you're trying to explain the apparatus and the procedure on a quiz or an exam. So notice the similarities and differences. It has the sprayer. Whoops. It has the sprayer. It's called an atomizer. It creates the oil drops. There's a little hole in the top plate. So this is a metal plate. This is a metal plate. And in this case, they're showing the voltage source. And that arrow means that it's an adjustable. Here's the viewing scope. And notice in this one, there's no radiation source. Okay, here's the Millikan apparatus. Take a look at this. I'm not sure how big it is, but judging from the photographs I've seen it in, it looks like it maybe stands a foot to 18 inches, 40 centimeters, 40, 50 centimeters high. It's fairly large, quite a bit bigger. See what parts that we just discussed are visible in this diagram. Identify them and kind of imagine in your mind or picture in your mind what might be inside of it. Okay, remember to pause the video and do it. Don't just watch the video. It'll be much more learning for you if you watch it in an interactive way. So the one thing that's clear, the only two things to me that are totally clear is the sprayer, which sprays an oil here. So I'm imagining this is the chamber and that the plates are down here. We can't see inside, but there's got to be two plates there. And the other thing that's obvious is the viewing scope. Now, what is this wire? That could be a wire carrying um, probably carrying the high voltage that goes to the plates inside wherever they are. These, we don't know what they are, but they are ways of pumping air or in or out of the chamber. This could be the radiation source, but we're just guessing as far as that goes. Okay, let's look at our own apparatus now. Okay, here's the apparatus that you will use or have used. Go through, it's a little blurry, but I think you can see it, and just identify everything. Go through everything and see if you can identify it. Spend a couple minutes and then turn the video back on and I'll go over it with you. So make sure you try to do it yourself. Okay, here we go. There's the oil. You didn't see that, but I saw it, that I filled the oil and it has a known density. So that's the sprayer. You squeeze that to create pressure that blows the oil out in a fine mist. That goes in the little hole in the cover and sprays the oil into the chamber. On top of the chamber, you see the plug. That little plug, it didn't show up in the diagram, so that keeps the little hole from getting clogged with wet oil. And you see the brass plate, which is the top plate, but we can't see inside the chamber. We'll look at that later over here. Here's the eyepiece that allows you to see the oil drops and the grid lines. There's a grid line structure in the eyepiece. So you have a focusing for the grid lines and a focusing for the wire in the center of the chamber, which means the oil drops will be focused on. Here's the light source that illuminates the oil drops or the wire from behind. It goes in here. And here's the power supply for the light source. Here's a leveling bubble that you use to level the apparatus, although we didn't make a big deal of that. It's not so important, but you could level it. Up here, they're hard to see, are the two plugs for the meter that measures the resistance of a resistor, which is the thermometer. Maybe you didn't remember remember that. Here are the two holes that will mount on the stand, and you can tighten those nuts so that you can raise it up and down to put it at a more convenient height. Here's the switch that turns the plates off or on with one plate positive, say the bottom plate positive or the bottom plate negative. You can flip this switch back and forth, so there's a 3-position switch. Here's the 3-way switch where you have the normal viewing position. You have the middle position that opens a vent hole, so when you spray it in, the oil will go in. So you slide this to the middle when you spray, and then you slide it back down. Or even better, you slide it to the middle, you spray in, then you slide it up to the higher position, which opens the radiation source and will put more charge on the oil drops than just the spraying gives you. But when you're viewing, you want the position here. So that's the viewing position, that's the spraying position, and that's the ionizing radiation source position to charge the oil drops. I think I got everything. Okay. Okay, here's another photograph. So take a look at this and see the other features of the apparatus that weren't shown in the other figure, and see if you can remember what they are and what we use them for. Then once you've taken a minute to do that, come back and I'll explain. Okay, so what we see is the apparatus lifted up on these two stands so that you don't have to bend over quite as much to look through the eyepiece. What you also see are the 2 meters that we used in the experiment, and the power, the voltage, the high voltage, the 300 volts that was put across the plates, for us wasn't a separate box, but there was a wall outlet. Remember, there's an outlet on the wall, and so we took 2 wires that connect to the plate voltage and connected them to the wall. That's where we get the 300 volts. And one of the meters was used to measure that because you do need to know the voltage. The other meter, you can't see the wires in this picture, but attached to the temperature sensor resistor up here. So we had 2 meters, one reading a resistance, which was really our thermometer, and the other reading the plate voltage because we needed to know the plate voltage to be able to calculate the drop, the charge on the drop. Okay, take a look at this one and identify all the parts and see if you can come up with the function of each part. So spend a few minutes doing that. I know the type isn't very clear, but yeah, so do that and come back and then I'll talk about it. Okay, what you see here is the chamber, which contains the area where you spray the oil. And from that upper area in the chamber, the oil will pass through this black plug, through the tiny hole in the top plate, and into the chamber between the 2 plates. So the 2 plates are what the voltage is connected to, and that creates a charge and an electric field between the plates. So we needed to know the distance, the separation of the plates, and so you measured the clear plastic spacer because that was what separated the 2 plates. And it's clear because you have to see into that hole. That is the space where the oil is, right? It's a tiny little space, but it's magnified by the eyepiece. So the oil drops go through the top, they swirl around in the chamber, they find their way through this plug, this black plastic piece, through the little hole and into this area of the chamber where they either fall when the field is turned off or they go up when the brass plates are charged or the voltage is turned on to the 2 brass plates, right? And the voltage creates the electric field, and the electric field creates the force on the charges, the charged oil drop that makes them go up. The black cap is to keep the tiny little hole from getting clogged with liquid oil. So the only thing that can get through the black cap is the fine mist of oil drops and not the heavy liquid oil, because that would clog the little hole and then the oil drops wouldn't be able to get into the chamber. This is actually the viewing chamber right here that you look through this hole, through that plastic spacer into this chamber. That's where you were seeing the oil drops, and those are the two plates that when you turn the voltage on made the oil drops go up or down. Okay, that was the easy part. Now the physics, and how do we take those measurements that we did, the measurement of the voltage and the plate separation and the distance the drop fell and the time it fell and the distance the drop rose and the time it took to rise. And what else did we measure? The voltage across the plates. And we didn't really use it, but we measured the resistance of a resistance thermometer. Okay, so the place to start is to make sure there's 4 situations, and we only did 2 of them in lab, but you want to, in doing the assignment, understand the 4 different situations. So one is the free fall, where the object falls in the absence of any voltage being applied, any charge being on the plates, any electric field. It's just falling without any electric force or electric field being applied. Then the second situation is the forced up situation, where you flip the switch one direction or the other to make the drop go up. So then you force the drop up. The thing that you didn't do is that we could flip the switch. If the switch to the right made the drop go up, the switch to the left, not in the middle, but to the left, would force the drop down. So we want to consider that situation. And the last situation that we didn't do was if we had the drop going up and we were able to lower the voltage, we could make it go up slower and slower. And so we would lower the voltage until the drop was suspended. So what you want to do is identify all the forces acting in these 4 situations. This is also an assignment question. Actually, I think it's in the lab. So try and do those 4 free body diagrams and then come back and you can watch me do them. Okay, compare your diagrams to mine. Let me get my pen. The force making the drop go down is the force of gravity, which is mg. And the force up, so what I didn't mention, and it's essential, you got to know this, is that when the drops move up or down, they move at a constant velocity. That's an important feature that I didn't discuss, right? And so think back to when you were observing the drops. They didn't start out slow and speed up, right? And when you made them go up or down, they pretty much moved at a constant velocity past the grid lines. So that's important, right? That means that the net force in the y direction has to be 0 because there's no acceleration. So notice the 2 vectors that I've drawn are the same length. And what is the second vector? What is the vector going up? What is the force going up that makes the drop fall at a constant speed? It's the air resistance force. So you could call it F air or Fr for resistance force. And you've seen this equation. You don't need to memorize it, but you might memorize it. There's a 6 pi. There's this Greek letter eta. It's like an N with a tail. It's the viscosity of air. There's R. What's the R? The radius of the drop. And what's V? The velocity of the drop. That's why we needed to know the velocity of the drop. That's why we measured the distance it fell and took the time. or the distance it rose and took the time. So we would get the velocity when it was falling and the velocity when the electric field was forcing it up. Okay, the second drop, the one that's forced up. So what's making it go up is the force on the drop caused by the plates. That's an electric force. It's the charge times the field. And we were given this relationship. It should make sense. We can't measure the field directly, but we can measure the voltage and the plate separation. That's why we measured the voltage and the distance between the plates. And so that's the force going up. The force going down is the force of gravity, but since it's moving up, there's also a force of air resistance down, right? The thing is moving up, so the air is resisting its motion, and so it goes down. And so notice that these two vectors are equal to that vector because when the drop rises, it rises at a constant velocity. Next, we have, if we forced the drop down, if we reverse the switch, we flip the switch from the far right side to the far left side or vice versa, then the force of the electric field would be down. The Fe would be down. Mg would be down, the force of gravity. But even in that case, it went at a constant velocity. So what is the force up? Like in the first case, it's the resistive force of the air. This same force, right? This force is acting down when it's going up. It's acting up when it's falling, and it's acting up when it's falling. And this falls faster, so this force is bigger. So remember, the length of this vector is equal to the length of these two vectors combined. Because it's moving at a constant velocity, the sum of the forces have to be zero. That's all our first semester physics, right? And the final situation is the suspending situation. This is the only case where there's no air resistance because it's not moving. So we adjust the voltage so it doesn't go up or down, it just suspends it. And so in that case, we have two equal and opposite forces. We have the mg, or the force of gravity, down, and we have the electric force going up, and they're equal and opposite. And it's this situation that we will use to try and derive an equation that allows us to calculate the charge on the drop. So this free body diagram and this free body diagram we're going to use. Now, the spreadsheet used this. So what I'm going to show you in deriving an equation for this situation is much simpler than this one. And you'll see this one is not exactly simple either. Okay, I'm not going to spend too much time on this. The document that's posted has the algebra worked out, but just see if you can do this on your own. We want Q. So I'm going to start with the lower diagram and use the usual method of summing up the forces and setting them equal to zero, because in every case, as we said, the sum of the forces is zero. So what we have for this situation is the sum of the forces in the y direction, right? It's vectors, so we do the components. Remember this? So we have qv over d minus mg force up, the force down equals what? 0. There's no acceleration. And so if you do the algebra, you get Q equals mgd over V. So that's going to give us the charge on the drop, only there's one thing that we don't know, and that's the mass. So how do we get the mass? We have to use this diagram. So write the sum of the forces in the y direction for this diagram, and see what happens. Come back. So just to remind you, we have this equation, and we know G and D is the spacer, and V is the voltage across the plates that we measure with the meter. So we're only missing M. So if we take this, the sum of the forces have to be 0 because it's moving at a constant velocity, and we get this equation. And if we divide it by G, we would have M. So we could take this and substitute it in there. The only problem is we still have R. R is the radius of the drop. So we don't know either M or R. So the third equation is the density equation. I'm going to pause. So don't wait for me. Jump ahead and see if you can solve this. This is just algebra. It's good to practice your algebra. So anyway, here's the density equation. Rho, we use for density, equals mass over volume. So mass is rho times V, and V is 4/3 pi r cubed. So if you're thinking about algebra, what you might do is eliminate the r and get an expression for M and substitute it in here with no more unknowns. But the algebra turns out to be a mess. So what's better is M is equal to rho V. This is V. So take rho times V and substitute it in for the M and solve for R, the radius of the drop. And once we have the radius of the drop, we can calculate the volume and get the mass. So it's better to do it in 2 steps. So see if you can eliminate M from these 2 equations and 2 unknowns, R and M. Eliminate M and solve for R. Try to do that. Okay, I'll show you the intermediate step. M equals rho V, that's V, so I put that there. So M is rho times V, and using this equation, M, I divided by G, is equal to that. So M is equal to this, the 2 equations, we can set these 2 equal to each other and solve for R. That's the last step of algebra. See if you can do that. Okay, here it is. This M is equal to this M. Now notice there's a pi on both sides. There's an R here. This is R cubed. So if I cancel this R, this becomes R squared. And then I multiply both sides by 3/4. Cancel that. And then I divide both sides by rho. And I'm left with R squared. So R squared, 6 times 3 is 18 over 4. That's 9/2. Eta V, rho G. Viscosity of air, the velocity, we measured the distance and the time, so we have that. The density of the oil, we have that. This is 9.80, we have that. So we have all these numbers. We can calculate the radius of the drop. And then using the density of the equation, we can calculate the mass of the drop, and you'll be asked to do that in the assignment. And once you have the mass of the drop, then you can calculate the charge on the drop. Okay, that's it. Get ready for the quiz. Bye.